Okay, so today we're going to start plugging algebra holes. I am starting the first part of the course as a fairly low math exercise because I want as many as possible of you to have gotten as far along in your math classes as you can, but especially those of you who are not taking pre-calculus or calculus. So if you are in Algebra 3 or something else, I want to make sure that you feel as comfortable as possible with algebra. And even some of you in pre-calc and calculus, you really will need kind of the exercises that we're going to do. So I want to go back to this idea of what is physics. And so far from the videos we've watched, we know that physics underpins every other science. Now, I decided at the last minute not to have you watch this particular video, but hopefully you picked it up from the Big Bang Theory, as well as the Physics is Life video, is that, physics basically explains everything that we encounter with the real world. And interestingly, even newborn babies have correct ideas about physics and how it works. And if you're curious about that, ask me when I'm back next week. So the question is, if physics is all around us and even babies understand some physics or physics at some level, why is it so hard to learn? And so I've been thinking about this for decades, and I have a couple of ideas. So, for one thing, as a school subject, it really does require understanding and not just memorization. I know every teacher says that about their subject, but it really is true for physics. It requires being able to apply much of the math you have learned from the past 6 or so years of schooling. And usually we don't go back that far in a subject matter. So if you don't recall and can use all of it as easily as you can go from school to your house, then you're going to struggle. It also requires using multiple areas of your brain simultaneously and well. It requires abstract formal logic. So this is reasoning with symbols. The bad news is that formal logic is something humans develop. The average human will develop sometime between the age of 16 and 18 years old. So some of you literally may not have the physiological connections in your brain that you need in order to do physics well. But don't despair. We are going to work on that very intensively this quarter, so that we're going to try to jumpstart finishing up all the brain connections that happen as people grow. This is not your fault. It's just, it is how the brain works and just the variation in growth and development. And then another thing that is really essential about physics is being able to recognize similarities between situations that look completely different. So I'm going to give you 2 examples. So one of them is just symbols only. And so I have 3 different expressions, and I want you to tell me if these are the same or different. But I want you to talk to the person sitting next to you or across the table before you answer this question. Okay, so as it turns out, all 3 of these are the exact same expression. There literally is no difference in any of these expressions. And if you can either plug in numbers to demonstrate that I am correct, or I can show you next week. All right, so that's mathematics. We've got another one. Are these problems the same or different? So, and read through them and discuss with a peer before answering. So these are actually identical problems from a physics standpoint. They use the exact same solution approach. We know 2 velocities, one velocity is 0, and then another one is the value given. We are given a time duration over which these 2 velocities changed, and we are asked to calculate a distance. So these are literally identical problems. And that's one of the things that I want to be able to teach you, is to recognize that these problems are the same, so that you will not even have to think about it. You automatically know how to solve them. And whenever you see a problem like this, you instantly know how to solve it without thinking. And so recognizing similarities, recognizing these are the same means that you don't have to come up with a whole new problem-solving approach. Recognizing these are the same arises from recognizing similar visual, mathematical, and linguistic structures. And then solving these same problems means using the same symbol set. And this is the formal abstract reasoning piece. So as I said, recognizing these are the same just makes it much quicker for you to solve problems that are literally the exact same problem, even if the externals are different. So physicists are really good at being able to classify things as the same, not the same, and the same but not the same. So there are 3 different categories of things. And it doesn't matter what level of physics you are on, success depends, or part of success depends on being able to sort problems this way. So we've seen word problems, experimental setups. So if physicists in Illinois are doing an experiment similar to one in Egypt, you need to be able to identify, are these experimental setups the same, not the same, or the same but not the same, so that you can compare results and try to make generalizations. And it's also real life phenomenon, and it really is the basis for all physics knowledge. Physics is the study of change in the universe, so you need to be able to identify when something has changed and is different. So we're going to develop a thinking tool, the same, not the same, or the same but not the same. And to help us develop this tool in our minds, we are going to use a set of representational tools for visualizing and communicating when something is the same, not the same, or the same but not the same. So we're going to develop brain structures that you may or may not have. We're going to start with very simple situations so everyone can feel some success, and they will gradually get more challenging. But even those of you who are in Calc AB or Calc BC, don't discount the effectiveness of the easy examples in promoting expertise. That acronym is the same, not the same but not the same. It's like skipping the warm-up if you're a musician or an athlete. Your performance is going to suffer in the long term if you skip the warm-up. Okay, so everybody needs to do this. So, example tool. So we have, or example 1, so our conceptual tool, are these the same, not the same, or the same but not the same? So again, talk to the person next to you, and I should have mentioned that we are looking at quantity. Okay, so in words, we would say a group of 3 dots is the same as a group of 3 dots. So in other words, we have the exact same quantity. So in symbols, we would, this one is, you can either have it there or not have it there. These parentheses means that I have a group. I've got 3 and the D is dots. And is the same as is my 3 lines. And then I've got, again, this one doesn't have to be there, but the parentheses have to be there because that indicates a group. And then we have 3 dots. So as the basis of algebra, these 2 diagrams are exactly the same because they have the same number of dots. So both of them have 3D. All right, let's do another example. So again, talk to the person next to you. Are these the same, not the same, or the same but not the same? And so our words, one group of 3 dots, and we've got is not equivalent to one group of 4 dots. So those are words, and these are symbols. Again, the one doesn't have to be there. I've got a group, and then I've got 3 dots is not equivalent to one group of 4D. Okay, so 3D is not equal to 4D group. So as the basis of algebra, these 2 diagrams are not the same. Okay, so I'm going to do another one. So are these the same, not the same, or the same but not the same? Talk to the person next to you. So in words, what we would say is that 2 groups of 2 dots is equivalent to one group of 4 dots. And the way that we would express that in symbols is we've got 2 and then the groups of the parentheses of 2D is equivalent to 1 group 4D. Okay. So as the basis of algebra, these two diagrams are the same, but not the same. Okay. All right, so I've got, you might want to stop and jot this down. So, because we're going to do exercises. So we've got a dot, the word we would use would be dot, and the symbol would be a D. A boundary like this, so an oval would be a group, would be the word, and this symbol would be the parentheses. And then something the same, words, a group of 3 dots is equal to a group of 3 dots. And then we've got 3D, I think that might be 4 lines. It should only be 3 lines, parentheses 3D. And then not the same, we saw what that one looked like. And then the same, but not the same. So on the homework, you are going to be given 2 situations. So say I have, this is situation 1, and this is situation 2. And in words, you would write out 2 dots. I'm not going to say a group of 2 dots because I don't have an oval around those 2 dots. And my symbol would be 2D. This one would be 3 dots. And this would be 3D. And then I would say these are not the same. And my explanation would be 2D is not equal to 3D. So you need to write everything out. Again, we're activating, I will go through this more next week, but we are activating different parts of your brain. And so your homework is going to consist of these 3 things. In some instances, I will give you the dots. In other instances, I will give you the writing or the words. And in other instances, I will give you the symbols and you'll fill in the other 2 columns.